Cool. I'm assuming that's, just double check. Sorry, yeah. Okay, cool. Welcome everybody. Sorry for that little glitch. It seems I managed to upload my entire session without any audio. So we are now going to be doing it live. If there are any kids screaming in the background, I apologize for that in advance. We have got 2 small toddlers in the house. So today's talk, resiliency and availability design patterns for the cloud. So let's kick this off with showing you an interesting scenario. Oh, by the way, for those who didn't join the previous session, my name is Cobus Bernard. I'm a senior developer advocate for AWS, but let's rush and get the presentation going. Cool. So who can guess what is going to happen over here? There's a user. He's busy walking down the road. That represents your average user with your application. And he's trying to do something in the application, and it's not quite what we expected to the application to do. So he's trying to do some kind of workaround, and oops a daisy, something goes wrong. But it's not just his little portion of the app that goes down. It's a nice big cascading failure, because you can see the barrier is down, the street is now being blocked. It's a bit of a fun situation. So what do we learn from this? Well, distributed systems are hard. Going with a distributed system is something that shouldn't be a light decision, but if you do need it, they are difficult to do. And hopefully with some of the things that I show you here today, it'll be a little bit easier to build them in a resilient way and in an available way. So looking at a quote from Amazon.com CTO Werner Vogels, it's failures are a given, and eventually everything will fail over time. So what this means is that no matter how well you build your system, at some point that system will fail. Something will break inside it. And then just quickly a definition, resiliency. That's the ability for a system to handle and eventually recover from unexpected conditions. So you'll often hear me speak about this term, a degraded system versus a broken system or a down system. And there's a very nice video that illustrates this. And this is what is known as partial fail mode, which is we've got a 3-wheeled little car, I'm assuming it's a little motorbike in the front, and the one tire broke. But instead of stopping, the system still keeps going. It might be driving a lot slower while they swap out the tire in process, but the system isn't down, it's still operating. And this is what you want when you start building your systems, is you want to be able to handle these failures where certain parts of the system might not be available, but as a whole, the system is still there. The worst example I have here is that I came back from a trip once late at night, and then my daughter woke up at 3 a.m. and decided it's playtime. And I decided, okay, fine, let's play and do some admin. So I opened up my banking app, and they had a nice warning message there saying, sorry, we're currently in a degraded state. Some functionality might not be available. What that actually meant is that you can do a search for ATMs and you can do a search for branches, and that's it. Everything else was off. So it wasn't a degraded system. It was an offline system. So let's quickly go look at why we want to build some resilient software systems. It's not just about the fact that we don't want our systems to be down. If you go look at some of the numbers behind the cost of having downtime, you can see the report that the numbers come from at the bottom of each of those columns. It's a very, very expensive thing to have downtime. So you want to try and minimize downtime as much as possible. So let's ask the question, how do we build resilient software systems? Well, the answer is not just here's a silver bullet, install this one app and you're done. It's a little bit more complex. The first thing is to understand that building a resilient system actually consists of a couple of different layers that you have to focus on. The first part being the infrastructure. You need to know what your infrastructure looks like and how it was designed to be able to build your system to make use of it. Do you have 1 server? Do you have 5 servers or 10 servers? How is your app actually distributed? The next level up from that is you need to understand what the network topology is and layout looks like, and also your data and how your data is stored, how you access your data, and how it moves around inside that infrastructure that you've got and the network you're using. The third section is the actual application portion. And this is how you design your app to actually make use of all the layers beneath it. And then the last one, which a lot of people actually miss, is the fact that you have to figure out how your people react to this to be able to build systems that are resilient. And at the end of the talk, we're going to take a quick look at a little bit of chaos engineering and how you can get started with that. So this basically is how you design for resiliency. So let's start off by talking about availability and what that actually means. So typically when you talk about availability, it's defined as the normal operation time over the total time that the system is up. We tend to measure that in a certain number of nines percentage. Apologies, I just need to mute this. Cool. And if you look at that, another way to look at it is the mean time before failure, because as we know, all systems will fail. And then you look at that as a percentage of the mean time before failure along with the mean time to recovery. And the important thing here to take away is that mean time to recovery is something that you need to optimize. Because if you can make that recovery time very, very short, then it'll look like your system is up the whole time. And a little bit of reading homework, you would have seen this in my previous talk as well if you were there. Going to focus more on the second book this time, which is Go Read, Accelerate. It's basically a scientific research explanation of how they go about doing the yearly the state of DevOps report, and they tell you how they set the questions up and how they figure out what is important to make companies move faster. So please go read this. In there, they've got a very big detailed description about how mean time to recovery is more important than just, for example, the number of bugs you have in production. So let's talk about availability. If you think, and sorry, there's going to be the same equation on this slide and the next one, and then no more math, don't worry. What it boils down to is if you think about increasing availability, and using an example we should all be familiar with is an elevator. If you've got a single elevator in a building, if that elevator breaks, you're stuck. You're going to have a long downtime until the repair crew comes out and actually fixes it. Whereas if you've got two elevators in parallel, if one goes down, then sure, it's going to be annoying because the other one's going to be a bit overloaded. But once again, it's a degraded system. It's not a broken or down system. And if you look at the math behind this, if you've got one component, let's say this elevator, and it's got a normal availability of 99%, that would imply that per year, you're going to have 3 days and 15 hours of downtime. If you just put a second one in parallel, you're able to take that to 99.49s, and that gives you 52 minutes of downtime. And if you put a third one in parallel, it means that you're going to be sitting with 6 lines and only 31 seconds of downtime. And that's literally just putting 3 elevators instead of 1, if you have, like I said, a availability of 99%. So that's something to take into account when you build your infrastructure, and you're going to see why that comes out when we take a look at what Amazon's infrastructure looks like. So you want component redundancy because that increases your availability significantly, especially when you start hitting 3. Once you go to 4, then it starts tapering off in terms of how many more you get for each additional one that you deploy. So just quickly what our global infrastructure looks like. Just to clarify the terms here, because they do differ from some other cloud providers, is that we define a region as a set of 3 or more availability zones, and then a single availability zone, when we start zooming in, consists of 1 or more data centers. And if we want to put some numbers to this, because I know people always love to hear about numbers, our largest availability zone has got 14 data centers, and our largest individual data center has got more than 300,000 servers. So that gives you an idea of how it works. But basically what it boils down to is that you'll hear me talk about deploying an app in a region, and then we refer to deploying hopefully at least 3 copies of it, 1 in each of the availability zones. Now, important to note about these availability zones is that we don't just take 3 data centers that are sitting right next to each other in terms of location. We take them with a meaningful distance between them and isolate them, specifically on the power level in terms of having different power providers. And also we take other considerations into account, like is there, for example, flooding prone in one area, then we try and put the other 2 where there is no flooding. They're still close enough together so you can do synchronous operations, and that means that the distance between them, when measured in milliseconds, is between 1 and 2 milliseconds. So typically, like database synchronization, all of that is fine. Then also with these AZs, we create a very large mesh network between them with a lot of additional redundancy. The reason obviously is that we need to be able to handle failure if there was some kind of partial failure in one of the availability zones between the buildings, or if a cable gets cut. So there's multiple very high throughput networking between them. So this is how you start understanding the infrastructure that you deal with when you build on AWS. So when you start drawing this in a diagram, you can typically refer to availability zone A, B, and C. Some of them go up to F. And like I said, remember 1 data center or more per AZ, and then 2 or 3 availability zones minimum. So we did initially launch some of the ones due to certain like geographic restrictions with only 2, but any new region that goes live always will have 3 regions. We actually even launched a third region, a third availability zone for Canada recently, which only launched with 2. So now let's take a quick look at global architecture and how we are going to be building our first app. So let's say you decide to build a new app and you deploy it on the East Coast of the US, and you get some users in the US and everybody's happy because they are close to the app and you are able to handle the load. Then after a while, the app is popular, and then the landscape looks slightly different. If you look at just the US vertical, you can see that there are now people using it from Canada and people using it from South America. Now, while they might not get the optimal, let's say, latency to the app because they are a little further away from the app than the other users, for example, in the US, it's still usable for them because they are able to get a decent ping and everything works well. Then what happens is the app becomes even more popular and it starts going global. And now this is where the problem comes in with latency. Because if you look at the latency between the US and, for example, the East, you're talking about 300 milliseconds round time. And remember, this is based on the speed of light because your data probably travels through a fiber optic cable that uses a laser. Laser is based on light. Light has got a physical limitation on how fast it can go. So there are limits, and we can't make this faster at the moment that we know of. So the question comes, how do I improve the latency for my end users? Well, the answer there is still have that original deployment there in the US, serve the people in the US, but then deploy a second version of the application in, for example, Europe somewhere, and that serves the people in Europe. Now, granted, the person connecting to Europe from Australia is still going to have a long-ish latency, but at least it's a lot better than trying to do a round trip literally around half of the world. So now let's see how that same design actually improves availability and disaster recovery for you. It's not just about the end user experience with regard to latency. So let's say we put the app deployed on both the west and the east coast of the US. Now, for some reason, there's a service on the west coast that starts going down. And ultimately, what will happen is if you didn't design your app properly, the entire west coast or the set of users from San Francisco will no longer be able to actually access this application. But let's say you set your DNS correctly and you did some kind of health checking in there. What you can do is you can redirect your users automatically to the east coast deployment of your application. Now, while once again, this is an optimal one for them because it might be a bit slower, it's still better than an actual app being down. And how you can do this is on the DNS level, you can set health checks and also do latency-based routing so that it decides where's the closest server to me. And then let's say that West Coast fell over, your application automatically recovered and redirects users to the East Coast version. Now, obviously, with DNS, there's always a little bit of lag to this, but still, it's better than the entire app going down for every single user globally. So the question that normally comes up is, okay, cool, this sounds awesome. This obviously means it'll fix all our issues that we have, but should we go for global architecture immediately? And the answer there is nope. Perfect your regional architecture first. The reason for this is that it doesn't help if you rush to deploy globally, but each of the areas that you deploy to keeps falling over because then you're going to have cascading failures. Because let's take that previous example where we didn't design our application properly and the West Coast fell over. Then all the traffic shifts to the East Coast. And then probably because it can't handle the traffic, the East Coast will fall over. And then you redirect all your traffic over to Europe. And then the European server starts failing. This is not something you want to do. You want to try and limit that blast radius. So don't go for global architecture first until you've actually perfected and worked a lot with making your regional architecture more robust. Let's quickly talk about the benefits of using this 3 availability zone design. So when you start looking at, for example, a multi-AZ architecture, so AZ is short for availability zone. This is typical design that we see is where you've got 3 instances of your front end running, and that connects to a database that is set up in a primary and secondary with a standby node. So what happens here is, let's say in the event of catastrophic failure, an entire availability zone goes away. What will happen here is that the load balancer will see that the health check to that instance is failing. And I remember this availability zone can go away for many reasons. Let's say just multiple cables are cut or the lightning strikes the building. And that actually did happen in 2011. So it figures out that don't send traffic there anymore. But now the application still tries to communicate with the database, which takes a little bit longer to do a failover. But because we set our database up across multiple availability zones correctly, it'll actually also then fail over to the standby. And then our application still keeps on running. So yes, a couple of requests might have been dropped, and our app is now in a degraded state where we have to deal with the additional load on those 2 availability zones. Our app is still up, it's still performing, and still able to service requests. So that's an important takeaway here. What you also get with when you start thinking about multi-AZ architecture is it allows you to easily enable or build fault-tolerant applications. And we as AWS actually build all of our applications with this in mind. And we spread our services across these. If you want to have an instant read, we released what's called the Builders Library recently, and there's an article on static capacity planning, and it tells you how to actually plan for having additional capacity available in all 3 availability zones so that should one go down, you're able to handle the traffic in the other 2. So you always have more headroom than you need just for the current amount of traffic. So another way to make your app a little bit more resilient in a very easy way is by using autoscaling. Now, typically, autoscaling is known for being used in this scenario where you've got a fixed base load per day, and then during the day, you scale up and scale down with the instances based on how many you need. But what's nice here is there's a nice benefit to it where you can actually scale your application if you don't need this elasticity. And what you do there is you set the minimum count to more than 1, so 2 or more. What this does is similar to that previous example I showed you, is that you deploy 2 copies of your application in 2 different availability zones. And then for some reason, the app either falls over or that server's hardware is deprecated and it gets taken offline. But then while that happens is the load balancer just sends traffic to your other instance while it's still running, spins up a new one, and ultimately once it's healthy again, you can then start sending traffic to it. So this is a very, very easy way. If you've got let's say a monolith that you're running, or just one copy of a service or application of some kind, just spin up a second copy. Now, obviously it needs to be stateless, but you can use, for example, sticky sessions inside the Elastic Load Balancer should you want to. But it's a nice, easy way to get extra resiliency for your app, literally by just running 2 copies with almost no extra effort. So making your apps a little bit more resilient as well requires you to understand what responsibility are you taking on. And what I'm going to show you here is just like how AWS views that responsibility model. Now, if you look on the left top, you'll see that we've got on-premise virtual machines. Now, let's say that's what you're deploying. That also means that you're responsible for the actual data center, which means electricity, cooling, connectivity, etc. Then you're responsible for the actual physical machines. You probably need to have a second backup copy if that one machine does go down, some kind of disaster recovery strategy. Then you are responsible for the operating system running on that machine. Then for the virtualization layer on top of that, and then ultimately what VM is running. And then inside the VM, what applications you're deploying and making sure that those applications stay up and running. So you're taking on quite a lot of the responsibility, and obviously that takes a lot of time. If you start moving to the right and look at Amazon EC2 instances, you no longer have to worry about the actual data center or the physical hardware. You just worry from the VM up. Is the host patched? What am I running on the host, etc. You can move all the way to the right, for example, with Amazon or with AWS Lambda, where you only write your little function code and then we take care of the rest. So think about when you're building your systems, what kind of responsibilities you want to take on and which ones of those you want to actually be responsible for making your app resilient. Because remember, the more you take on, the more you need to know about all those systems. So just think about how to make your systems more resilient. So now, how to make your databases a little bit better. First one that I want to go through is that what are the common issues that we have with databases? The first one that most people will hit is some kind of scaling problem. At some point, your database simply can't handle the load anymore, or you might have a very badly written SQL query and it just isn't able to handle it. The second problem that people run into tends to be around replication, because that's one of the ways to shift load and also have a copy. But if that replication lags too much, you're not going to have a fun time. And then lastly is backups. And this is where I normally get a little bit of audience interaction, because I always ask, can everybody who's actually checked their backup that it works in the past week raise their hand? And typically it's, okay, there's one person at the back, did that backup actually work? So yeah, go test your backups, make sure that your backups are working. So just quickly, a very interesting read is the design behind DynamoDB. Don't worry, this is not a product pitch. We hear about architecture principles, but the way they built it is they split the compute and the actual storage layer. So it makes use of S3 under the hood. And then when it does a put item, before that put returns successfully, it actually writes it to 6 different locations across 3 availability zones minimum. So it means that you know that that data is sitting in at least 3 of the availability zones. The benefit here from the resiliency and also from the performance and availability is that, let's say I want to now read that data. I'm able to read it from my local availability zone where that code is making the request from. So if for whatever reason, let's say the top availability zone wasn't available and the app only had 2 copies running on AZ, B, and C, each one of those would be able to query the data locally because it's there. And now you're once again in a degraded state. You're not in a broken state. Good thing. And also just quickly, some stats just in terms of the performance. We had a lot higher numbers with last year's peak, but I haven't added it to this presentation yet. Next thing that I want to tell you in terms of how to make your apps better is use purpose-built databases. If you look at these different columns, the different types of databases available today. When I started developing, I had basically relational databases available and files. That was it. Any of these fancy different type of databases, while the theory existed because a lot of that came from the 70s, there weren't any practical implementations that I could use to code with. So if you think about the reason I bring it up is that let's say you've got a problem where you want to view the relationships between the different items. You're building some kind of recommendation engine, for example. Something like a graph database is actually purpose-built specifically for these kind of problems. And if you try and build that same recommendation engine using something like a relational database, which wasn't made for, you're probably going to have a weird data access structure on the database, and it's going to make it less reliable because you're going to be hammering it at certain times, and that might cause it to fall over. So pick the right database for what you're trying to do, and that'll actually make your app a lot more resilient just from the get-go. So let's look at how you can actually improve specific performances on a database. The first one is by just separating your read and write operations on the database. And typically how you would do this is you have some kind of application with, let's say, 3 copies of it running, and then all the writes happen to the primary node. And then what you do is you change your application, and this will require a little bit of coding changes. But then if it's a read operation that you're doing, you make those reads off the read replicas. Because that way, when you look at the overall picture, there's a lot less load on your primary database. So just think about this as a very easy way to, well, fairly easy way to start reducing the amount of load on top of that primary database. The second way is, if you've done this already and you can't get more scale out of it, is to actually do database federation. And this is where you start looking at the different tables inside a database that are heavy, and then you decide to split them between different database servers. So in this case, we've split the products and the users database. The second benefit with this is that you can also scale them individually. So let's say you see that the users database is having a lot more load and needs a much bigger instance. You're able to spin up just that one database and not have to also spin up the products database, which is then idling. So think about splitting on a table level. Then the third type, which is probably a little bit more on the complex side, is called sharding. And this is where you decide that there's some kind of key that indicates that the data has been is split into, in this instance, 3 different buckets, A, B, and C. And if we say, let's say, a surname, please don't use something like the first letter of a surname, because surnames aren't evenly and uniformly distributed across the alphabet. But if you did that, then you could say, listen, A to F is going in the first one, G to M is going into the second one, and because there's less, N to Z is going to the third one. Now, the things, if you do want to go down this road, immediately figure out how you will handle resharding. And what that means is that if we decide that this load is becoming too much for these 3 individual database servers, how are we going to bring on a 4th one? Because as soon as you bring on the 4th one, you need to change firstly the logic on how you do the sharding, and secondly, you have to rebalance the shards. So you have to move data from all 3 of them into the new 4 in total. Remember, that's going to put additional strain on your system. So think about how you want to handle the sharding and when it happens. Now, I did warn you that I'm going to have a little bit of a talk about databases. So figure out how you can make your database backups better. Because imagine you have to do some kind of performance maintenance check or just some kind of change to your database, and all of a sudden your database just falls over. You're now screwed. And what you could have is that if you haven't been testing your backups, you could, if you go read in 2019's news headlines, a couple of big well-known brands did have backups, but the backup files were empty, or they didn't even have backups because nobody bothered to test those backups. That's not a great scenario to be in, and you want to make sure that your backups work. Because on the other hand, this is a much better feeling, because you do that thing where, oh crap, you dropped the database. And I actually did this, not the dropping of the database, but on the second day of my very first job, I was given a task of saying, hey, there are people abusing the system. Can you please go write a query to figure out how to drop or lock those accounts? And I'm like, okay, cool, no worries. 3-4 hours later, I had a where clause about this big. I ran the select version and grabbed a whole bunch of records, compared them against the known abusers. We said, okay, cool, these are definitely the right set of people. So I'm like, okay, cool. Should I run this in production? They're like, yeah, run it in production. I'm like, okay, cool. Run the query. And then what happened is I saw 500,000 rows affected. And I'm like, we've only got 500,000 people in the database. And I'm like, oh crap, I've just locked everybody out. And what I've done there is actually to highlight the update table name, set locked equal to 1, and that entire where clause that I spent most of our time on didn't highlight it. Very bad. Good news here is that we did have backups, but instead of restoring the backup, we tried a different method by interrogating the logs, but we did have the ability to actually spin up the database. So please go do your backups. And also, when you do backups, don't try and do bash scripts or your own. Apologies, I've got a visitor. You try and make a use of a service of some kind that does this for you, because you don't want to spend time trying to perfect this. You want to spend time elsewhere to make your system more resilient. Another way you can actually make your database a little bit more resilient to failure is actually to protect the user from themselves. Now, if you look at something like, for example, DynamoDB, you can, with an iron policy, prevent people from dropping a table. And if you look at the code snippet on the right, there you can see an actual CLI call being made. And if you look right at the bottom, the second last key value pair, you'll see that the table state is actually deleting. And this was before setting this deny policy, which means that once you have this policy in place, you can't accidentally just drop a specific table. You can also do this with things like, for example, MySQL. You can add a trigger to a table to say, we are preventing you from deleting rows from this table. So what this means is that we're preventing any kind of delete. And then in the second code snippet, you can see there that when we do try and do a delete, we're actually going to raise an error and tell you, sorry, you can't actually do this delete. You're not supposed to. Use a flag here. Another reason to use a delete flag instead of actually deleting a row is that it actually allows you to get a bit better database performance, because deletes are quite expensive because you have to rebalance the index and figure out where that gap now is on the physical disk, etc., etc. Apologies, give me 1 second. Cool. Thanks. Sorry, just had to close the door. The little intruder has now left the room. So, important thing here is practice and test your backup recovery. So if there's nothing you take away from today's talk except that you want to go test your backups, I'll be happy, because that's one way you can make sure that you've got a mechanism to actually restore your database and actually have your system back up and running. Now we're going to get into a little bit of fun things, which is where we talk about timeouts, backoffs, and retries. And let's dive right into an actual example. So let's say we've got a user that's interacting with some kind of application, and that application has some kind of database connection pool. And you're making calls that does inserts to the database. What's going to happen when this database starts coming under load? Well, let's figure out. In this case, we have got timeouts available because most languages and applications have got mechanisms to set timeouts both on the client side as well as the backend side. So let's take a look at what's going to happen when we don't have those set, or how do we handle those. So let's say a typical example, the user starts making a call to the application, and that application tries to make an insert into the database. Database comes under load. Then obviously that query hangs because the database hasn't finished servicing it yet. On the client side, we've got a 10-second timeout set. But then on the application side, we left it as default, and the default is infinite. And if you don't believe me here, go look at your documentation. A lot of the database connection drivers have got a default of infinite. So that query is now hanging. Then on the client side, 10 seconds later, obviously it times out, and that user sees, oh, okay, cool, my connection or the request I made failed. So what do they do? Button mashing, click, 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 click. We're going to start hitting retry. So we hit retry. But if you look at that little red lightning over there, that query is still running because the application is trying to actually finish this insert. Then guess what? It spins up a second one. Same story. Tries to do insert. It starts to slow down. It keeps hold of the connection. The user times out, and we do it the third time. And then by the fourth time, this is just happens to be when we ran out of connections. And now you get that error on the front end saying, listen, sorry, no connections available, and the app is down. And it's probably down for everybody because the entire database is now locked up. So how do we go about making this a little bit better? Well, the answer there is actually go set those timeout requests. If you look at this as an example of C# in the .NET Framework 4.8, you can actually set the timeout on HTTP request. You can also set it in multiple different languages, or in, for example, your ORM software that you're using to connect to your database. You can also set that timeout value on the database driver that connects to your database and handles your database connection pools. So please go set those back, those timeouts, and then you can at least handle those long-running queries a little bit better. You can also, if you want, add them to your code. And you can use something like aspect-oriented programming, which you can do in Python and Java and a couple other languages, where you decorate your methods with specific timeout configuration. And this allows you to do fine-grained handling of specific requests, depending on what you want that application timeout to be. Because in certain cases, a 30-second one might make sense, but in another instance, a 5-second one will be more appropriate. So when we go back to our scenario that we had, there's another way we could actually make this better by not just setting the application timeout. What we can do is on the client side, we can make use of backoffs between retries. And what we mean by this is that over there, when I make my initial request that times out and took, let's say, 10 seconds to do, instead of immediately making another request and hammering the backend, I wait 2 seconds. Then if that one times out again, I wait 4 seconds. So I keep doubling it. So in this case, we're doing exponential backoff. And what this does is it gives that database time to actually recover. Because let's say we keep doing this. Then after a while, that we've added the timeout now on the back end as well. And that request might now have timed out properly after 10 seconds. And the next request from the client only came in after 12 seconds. Then second query comes in. And then ultimately, we might be able to get to a point where all of the connections have been released. The problem with this, however, is that if you look at this graph on the left, is if we only do this exponential 2, 4, 8, and 16-second backoffs, you're going to have clusterings of those requests. So let's say a whole bunch of customers are currently using the app. We're all clicking on the button at the same time. Then we do the call, it times out, and then we all wait 2 seconds, and then we click it again. You're going to see these peaks come out clustered around the specific timeout exponentials that you set at the 2, 4, 8, and 16-second marks. And this is obviously not ideal, but how we adjust for that is by adding some jitter. And what we mean by jitter is you do something like this in your code, where you look at the double the amount of the timeout interval, because remember, what you want to do is you want to be able to spread those retries between 0 and 4 seconds, because remember, you're going to have the cluster around the 2-second mark. Now you want to make use of anything before 2 seconds and also anything after 2 seconds, but before 4 seconds, because that then spreads it out. And if you go back to that previous slide, you can see there with jitter how nicely it's now spread out across the entire graph, which means there's a higher likelihood of your database being able to recover. Because trust me, databases don't like it when you go like, boom, queries, and then wait a few seconds, and then boom, queries. That normally makes them very, very unhappy and where they have performance issues. So the problem with this, however, is you also need to think about how is your application going to handle these retried requests. So you have to make your request idempotent. And what this means is that when you make a request for a second or third or fourth time, it still has the same effect as if you only made that call once. And a good example of this is, think of a banking system. If I make a request to deposit 50 Rand in my account, and for some reason it's lagging and I make that same request 4 times, I would be more than happy if the bank didn't do this and gave me 4 times deposit and actually gave me 200 Rand in my account. But the end result should be only a single 50 Rand increment to my account, not 4 times it. So think about how you want to build your operations to be able to handle this. Maybe when you do any kind of operation, you first send back some kind of GUID and then you use that GUID to actually make the request. There are a couple of ways to do this, but think about how to make your operations idempotent. So now the next part to resiliency is health checking. So I spoke about this typical layout that you have with, let's say, a load balancer that has got a couple of services and is able to make sure that the services are up by making some kind of health check call. Now, what often happens is that you've got multiple services, and each service has got a couple of downstream requirements. For example, some kind of cache, some kind of database, some kind of, let's say, mailing server, and ultimately some kind of other cluster that we are making requests against. What happens is that a lot of people just build shallow health checks. And what we mean by this is that it's literally, you've got a method, it says nothing in the body, it just goes return 200, okay, I'm healthy, yay, that's great. I also built these, so don't worry, you're not alone. What this means is that if this service requires multiple other services downstream, and something was broken, like let's say the database went down, what's going to happen is this instance is going to go, yay, I'm still happy, I'm still healthy, please send me a request. And every single request it gets, it can't service because the database is down for whatever reason. Might be connectivity, might be the database fell over, database overloaded, etc. What you do want to do is you want to have what is known as a deep health check. And in this case, what it looks like is that the instance is actually aware of what is the state of all the downstream services that it needs. So in the event that, for example, the database is no longer able to service requests, this instance then starts sending back to the load balancer saying, listen, don't send me more requests because I know I won't be able to service them. Because what's the point of getting more requests and just hammering the database further if you know you cannot make requests to it? So this is one way that you can actually make your instances a bit more resilient by doing these deep health checks. However, remember, these deep health checks will add additional load to your system because they're now making a lot of more requests. So what you don't want to do is health check coming in from your load balancer to your instance and then doing all of those individual health checks, and the initial one waits for those to complete before they go back. So what you want to do is you want to prioritize shallow health checks during hard times. And what we mean by this is by using cache. So those health checks for the downstream requirements that you have, cache those values inside your application and maybe only make those deep health checks every 30 or 60 seconds to check if they're still healthy. And then what you do is, based on that cache value, you return the top one return the summary of those based on what you have cached every second or 2 seconds when that health check from your load balancer comes in. So just think about that. Or you can go to a point where, listen, you increase the time between doing those deeper health checks if you see that your system is overloaded. Because remember, if you are dealing with additional load, if you can shut this off or reduce the number of deep health checks, you can easily free up additional resources to then handle that additional load, and you might not have any outages at all to deal with. So next part we're going to talk about is load shedding. And no, don't worry, this is not going to be anything to do with ESCOM. Understand that that's a sore point. What we are talking about is latency versus throughput. And if you look at the typical transactions per second throughput, the graphs tend to look like this, where up until a certain point, you're able to handle the request fairly in the same amount of time. But then all of a sudden, where your system starts struggling, you've got this peak coming up. And what you want to do is you want to optimize for that gap over there where you set the client timeout, where you know that you can no longer actually handle these requests. Because let's say you've done load testing, you test, and you know that on your service, and you know that you can no longer handle more than, let's say, 500 requests a second. Why are you even accepting that? So what you can do there is figure out how long the latency becomes for the request, how long do they take to service when you hit that point that's difficult. And then you can do that, use that to actually cheaply reject excess work. What we mean by this is that that line is that anything below that latency is what we accept, and everything above it is what's going to be timing out on the client side. So you can raise or lower this depending on what kind of customer experience you want to do. Because remember, the higher it is, the more customers will still get in, but the more of them that will have slow requests or request a timeout. So figure out where that sweet spot is. And what you need to do is you need to be very careful when you select the right metric for this. So figure out what's important to your system. It's not just, for example, CPU or memory stats at the moment. It might be something else more nuanced. So when you think of load shedding, don't be overly optimistic and set it too high. You want to rather set it lower and then slowly over time increase it a little by little. Because that way you can actually find that sweet spot where this is where we handle just enough so the majority of our customers are still happy enough to use our application. But if we do go above that, then we know we are shedding some connections for some people, but not the majority. So figure out, don't be optimistic, because if you start too high, your entire system is just going to fall out and all your customers will have a terrible experience. Now, I already mentioned that you want to find that operational metric that allows you to reject the work that reject the work that you don't want to take on. Also, during these times, favor those cache deep health checks and try and use static content as much as possible. Because remember, if you are serving, for example, images or static requests where you read the request for, let's say, the entire inventory system that you've got, if you can cache that somehow and only refresh it in certain intervals, that means you can reduce the load in your system, because then you get the request coming in, hit the cache, go out again, instead of come in, go to the database, hit the database hard, and go out again. So that's a nice way. Also, we spoke about how to prioritize those shallow health checks during times when you are under load. And also, just remember, design your system in a way where you can turn certain things off to actually reduce the load that you yourself cause for your system. Because when you do get into situations when you are overloaded, you can then actually make those resources available, and then the system might be able to cope with those additional capacity that you've just freed up. So now, for the fun part, is for chaos engineering or resiliency engineering. And this is a practice where you do fire drills. And I don't know if you saw in the news a few months ago, they were actually doing a fire drill at Cape Town International Airport, where they lit a part of the tarmac on one side, and then the fire marshals came out and actually dealt with it. So the whole point is you want to practice failure, because we know failure is going to happen. So it's better to actually prepare for it. And if I spoke to anybody now in the audience and I told you, hey, think about the systems you're working on at the moment, tell me one area, if that one service went down, will it take the entire system down? And most people will tell you, yeah, we probably know about that one, and that's the one that keeps us up at night when we worry about things. Go figure out how to make that one system more resilient. And one way you can do that is by implementing actual chaos engineering frameworks. So Netflix has one called the Simian Army, and it consists of a whole bunch of different individual tools. They start off with just Chaos Monkey. And what Chaos Monkey does is you give it an API key and secret to your AWS account, and then it will go and random pick one of the instances and actually just go terminate. And then hopefully your system is resilient and is able to spin up a replacement for it and deal with it. And that's how you could actually figure out, can my system handle some failure? Then they decided, okay, this is good, but let's, we now solve that problem. Let's see if we are actually more resilient than we expected. So they brought out Chaos Gorilla. What that does is actually tears down everything inside an entire availability zone. So if you've got those 3 availability zones with your code, everything in, let's say, A, terminate and delete. So hopefully you've designed your system to have database failover, multiple copies with additional headroom to handle the additional load while more resources are spun up, et cetera, et cetera. They took that one further and made Chaos Kong, which actually deletes an entire region. So everything in all the availability zones inside that region is deleted. They do this because they constantly shift between the US workloads and the European workloads when they do some of their backup failure testing. So they've got a whole other bunch of tools available in here, for example, introducing some latency, etc. So just for those who want a formal definition of what chaos engineering is this. Chaos engineering is the discipline of experimenting on a distributed system in order to build confidence in that system's capability to withstand turbulent conditions in production. You can see the URL that came from. And what this means is that you want to practice injecting failure into your system on the application level, on individual hosts that fail. Let's say your CPU becomes overloaded, a whole bunch of different ways to actually overload your system or break your system to see that it works. And there are a couple of frameworks available as well as commercial products if you look at the links at the bottom of that slide. Now, the important part here is that we don't want to give you permission just to go, hey, let's go break production, see what happens, and have fun with a tire fire happening. You need to do this properly and responsibly. So what you want to do is adopt the different phases of chaos engineering. And what we mean by this is that start off with a steady state where nothing is burning and nothing is broken. Then say, cool, I've got an idea, I've got a hypothesis. if I were to delete one of the instances in our autoscaling group, the autoscaling group should take care of bringing that back up. Or if we terminate our primary database node, we should be able to fail over within a certain time frame. So set that out. This is what we're going to test. Then run the experiment by doing what you were expecting to do. Then verify, was my assumption correct? Did the whatever I have in place work? If it didn't, you go ahead and you go fix it. Because what's the point of actually figuring out there's a vulnerability in your system in terms of resiliency and you don't go and fix it? Then you go back to the steady state. Then you go, okay, cool, we can now handle this. What else can we go do? And you keep running this loop over and over again. It'll take a bit of time to actually get to a point where it's resilient, but that's how you actually practice chaos engineering to make sure that your services are nice and resilient. And with that, I want to leave a little bit of time for questions. So thank you very much. If you have got any other questions, if you're seeing this at a later date, please ping me on either LinkedIn or Twitter. Those are my handles. Very easy to find me on the internet. And then also I will be streaming some live coding sessions on Twitch in the coming weeks once I've got my setup at home sorted. So if you've got questions there, please hit me up. I'm going to head back to Slack now and also take some questions over Zoom. So thanks for listening. Cheers. Cool. First question here is, hey, what would you recommend doing in the case where your one point of failure is another company? For example, an AWS array was asked. So remember, when you're using third-party services, you have to figure out what is their SLA, what is their track record, how good are they at actually handling failure. And the thing is, it says, because if you look at a company, you see that, listen, they seem to have downtime every second week and every third week, then I wouldn't want to rely on them. I'd rather go with another company or figure out how to build something possibly yourself if you can. But at some point, there's no, you can't build everything yourself nowadays, especially if you look at the cloud. The whole value proposition of the cloud is making use of managed services where someone else takes care of that with better experience and expertise than you. So let's say a managed database service. The uptime of something like, for example, RDS will likely be much higher than your own implementation of running something yourself. So don't try and build your own system from the ground up. You're going to spend so much time doing that and you're not going to get any features out, which means that, guess what? Your product's not going to go forward and you probably will have to start looking for a different job. Okay, there's a question here on Slack. Oh wait, there's a whole chat over here. So blah, 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 blah. Okay. Okay, no questions there. What I'm going to suggest now is I'll hang around in Slack for a little bit more. If anybody's got any further questions, just hit me up there. And also, I'm always available. Well, not always. I keep an eye on ZA Tech Slack. So if you want, come ask me some questions over there. Specifically, if you want some AWS information or knowledge, that happens in the AWS challenge. So what's monitoring your monitor? Hopefully another monitor. And unfortunately, it turtles all the way down. Okay. I am now going to say cheers and I will be available on Slack. So please continue with the questions and I hope you enjoyed this presentation. Okay, bye.